All right, this is lab 1.5. Our topic is going to be decomposition reactions. My name is Myles Pittman.
And I am Kyle Scott.
All right, so we're getting ready to go over to late night labs, and what you're about to see is the simulation. Now, if you go into late night labs and you click lab 1.5, you can follow along right with us and do the simulation as well. We're going to start off by weighing the crucible. I'm going to be telling you the procedures because you're not going to be able to read them because we're going to have the lab notes section open so you can read our calculations. Now, the crucible is 88 grams. All right, it's 88 grams. Now we're going to put down the Bunsen burner. All right, we're going to set everything up, which is also outlined in the procedures. And then we're going to add 5 grams of carbon-2 carbonate hydroxide hydrate to the crucible and weigh that. That gives you a total of 93 grams, which makes sense. 88 plus 5 is 93. All right, then we're going to move the crucible over to the Bunsen burner. And we're going to double click on the crucible so we can actually see the reaction taking place once we turn the Bunsen burner on. And once the solid inside the crucible changes colors because of the heat, we know that the reaction has occurred. And that's going to take a little bit of time, but once again, like I said, once it changes color, we know the reaction has occurred. All right, so we're still waiting on it to change color. All right, heat's being applied, slowly building up. And it has. All right, so now it's turned black, and there's mist coming out of the crucible. So we're going to move the crucible over to the balance to see how much it weighs, and lo and behold, we actually lost some mass, 91 grams approximately. And that mass, mass that we lost is now in the form of vapor, which escaped the crucible into the virtual lab setup, and that in turn is what a decomposition reaction is.
Okay. Here we have the decomposition reaction. A decomposition reaction is one where one compound, in this case carbon-2 carbonate hydroxide hydrate, is broken down into several other compounds or elements, oftentimes because energy is added, energy in the form of light, heat, or electricity. This occurs because the added energy breaks apart the bonds of the original compound.
In an open system like the one observed in late night labs where the crucible wasn't sealed completely shut, which would be a closed system, the reaction may seem to violate the law of conservation of mass, which says matter cannot be created or destroyed. However, if the new compound created takes the form of a gas, it may leave the system, causing it to appear as if mass was lost. If we were to collect that vapor that left the system and put it on the balance and then add it up to the new weight we got, you get the original 93 grams. That can also be demonstrated more easily easily mathematically. In the following slides, you'll be able to see that through molar ratios and molar mass.
Okay, coming up here we have the balanced chemical equation. First you have 1 molecule of carbon-2 carbonate hydroxide hydrate. When heat is added, you get 2 molecules of carbon oxide, which is the black solid we saw at the bottom of the crucible. You get 1 molecule of carbon dioxide gas and 2 molecules of water vapor. Those last two are what we saw exiting the crucible after the reaction had occurred. Here we have the equations which show the mass of the carbon dioxide gas and the water vapor that left the crucible. First we find the molar mass of each of the compounds, respectively. From there we take the original mass of carbon-2 carbonate hydroxide hydrate, which was 5 grams, and multiply it by the molar mass, 222.13 grams, to give the number of moles of that compound in the system. From there we multiply by the mole ratio of carbon dioxide to carbon-2 carbonate hydroxide hydrate, which is a 1-to-1 ratio. Then we multiply by the molar mass of carbon dioxide to give the total mass of carbon dioxide created in the system, which was 0.991 grams. We do the same thing to find the mass of the water vapor, this time using a mole ratio of 2-to-1, to give us a mass of 0.811 grams of water vapor. Finally, we subtract the masses of carbon dioxide and water vapor to give us the mass of the carbon oxide, which is 3.9818 grams, which, as we saw, was the case in the earlier lab when we weighed the remaining carbon oxide. That is all. Thanks for watching.